We placed 4th in the virtual robotics challenge, and as Todd said, we had about 4.5 months from getting our Atlas robot to participating in the competition, and we placed 6th in that competition among the 16 teams. This is our team. We have basically 8 people. We have the principal investigator, Robert Burridge, and a person in charge of basically facilities maintenance, and then about 6 programmers. So I'm the software lead. We have somebody that just works on the GUI, and then we have a handful of interns, various grad students and undergraduate students from universities around the United States. So we have a small team. We didn't have a lot of man hours to explore high-risk, high-reward strategies like some of the other strategies you may see here. So our approach was to do the easiest thing we possibly could for every task the robot needed to do. So we sort of see ourselves as the baseline. So what can this robot do using off-the-shelf algorithms that are out there, or very simple algorithms that we can develop quickly and integrate quickly? So for us, we saw the DRC as primarily a software integration problem, not a research problem. So as I said, we use off-the-shelf software when possible, and we rely on the human operator for all high-level decisions. So basically, this is very similar to what Todd was just talking about, the Team Trooper did. So we focused on the most basic software that we needed to overcome the control perception, remote operations, and networking challenges. So I don't think I probably have time to discuss Atlas in full, but this is here in case anybody cares later if you're not familiar with Atlas. But I would like to just note that in the competition, there was some pretty restrictive networking. In the worst case, you had 100 kilobits per second throughput with a 1 second latency to communicate with your robot. And so from a systems integration point of view, we spent the majority of our time in these 5 areas: networking, user interface, manipulation issues, perception issues, and mobility and walking, which I won't discuss perception, mobility, and walking today just due to time. So I'll really just go over how we approach the first 3. The simple, as I said, applications that we used to tackle those problems, and then how that worked out for us. And then I'll focus slightly on what we're currently working on. A lot of that is very similar to what you just saw from Lockheed, but without fancy pictures and graphs. So in networking, we actually spent quite a bit of time optimizing network communications to the robot due to the network restrictions imposed by DARPA. So some of these were straightforward, like you enumerate, you create constants to replace strings, you compress your images in various ways. But some things that we definitely did that might not be obvious, we never send raw point clouds from the robot to the user. They're just too large. So instead, on the robot side, it would take 3D point clouds, create a variety of 2.5D projections of those, compress them, pass those over the network, and then we would reconstruct the 3D point cloud on the user interface side. Additionally, the user could request different kinds of data at different rates, but there were specific defaults for tasks, so that if a user moved from manipulation to walking, those defaults would change and it would get new data at different rates. And of course, obviously, before the competition, we just put the network in the worst case scenario, and we made sure that we could achieve all the tasks that we wanted to in the worst case scenario. It turns out that, so because we're using a lot of off-the-shelf software, we're using ROS. It turns out that the default ROS operation wasn't actually useful. One reason is due to this network restriction, so you can't actually start up your nodes, go to a ROS master that has a 1 second round trip latency and has a very low bandwidth, and actually get any of your nodes to start up in time. So that was one issue. The other is that ROS sort of broadcasts data. You can't ask it to broadcast data slower. And so if you attach to a high bandwidth topic, you're going to get information at a high bandwidth. So we set up a dual ROS master system. Basically, there's a ROS master running on the robot computer, a ROS master running on the user computer, and we wrote our own very simple UDP network layer that links those two together. And so this also had data throttling, which we needed, that would only send the appropriate amount of data based on what the user wanted and the current profile of the network. So when the network was good, it would send more data. And we set up a round-robin message queue system, essentially, so that high bandwidth topics wouldn't starve out low bandwidth topics. So pretty simple, but took a little bit of time to iron out all of that to make sure that it really worked. The next item is a user interface. So we have a very simple user interface. This is essentially a single user interface. We only had one operator. And this is what it looks like when we go to start it up. So at the top, there's just connect and disconnect to the robot. There's a bunch of different actions that are pre-programmed, essentially joint scripts, and different things like ask the head to move the pre-programmed positions to look at different things. On the left, in blue, you'll see that we can get some status information about the current state of the robot, and we have feedback on various tasks that the robot may be doing, whether it's succeeded or failed, or how far along it is. And then, as I said, in the bottom left, you'll see that the user can define how fast it wants to get different types of data. And then on the right, in the green, is the task-oriented interfaces. So there's tabs at the bottom, and these are all the tabs that we used. Essentially, there's some joint control scripting that, like Todd showed, shows a simulation, allows you to see a trajectory and then execute it, and then some that are specific just for walking and manipulation. So I'll go through some of these just to show you how straightforward they are. Here's the multi-step walking interface. So in this, you simply get the camera's forward view, the robot's forward view looking down, and you get the 2.5D point cloud that looks at the XY plane in front of the robot, and the user can click a variety of points, ask the robot to walk along that trajectory, and then the robot will establish what footsteps are needed to accomplish that and start walking. We use this not just for walking forward, but for walking backwards, for dynamic walking, for quasi-static walking, for stepping sideways, turning in place, etc. Similarly, for a lot of what the robot had to do in the competition was manipulate items or tools in front of walls, like valves, drilling in walls, opening doors, etc. So we actually have a specific wall interface that takes the point cloud, extracts out the dominant plane in front of the robot, and only presents the user with the point cloud that fits that plane and that it can see with its sensors, with its cameras looking in front of it. And so this actually allowed the user, the same way you could click and define a path along the ground, here the user can click and define a trajectory with respect to the wall and define a distance away from that wall, and then the robot would execute the trajectory at that distance from that plane with its hand or with the tooltip if you asked it to use, let's say, the tooltip of a drill. Obviously, occasionally you need more precise interface for manipulation. So here we show just the reconstructed 3D point cloud, and we just use a simple interactive marker with an RViz plug-in here to ask the robot to move one of its hands or a tooltip to a specific 3D pose in the environment. One nice thing about this that we added to the interface was you actually also get a forward planar view and a top-down planar view that correspond to this point cloud, and little markers on that show you the X, Y, Z positions in those, which the users found helpful, instead of just presenting the 3D point cloud. And it turns out that that same interface we actually used a lot for walking as well. So instead of just commanding the hands to go to 3D poses, you can command the feet to go to 3D poses. And so for rough terrain, we actually, instead of just using the walking interface, we commanded the feet to go to specific locations and hoped that Boston Dynamics quasi-static walker put the feet in those positions. So pretty straightforward stuff. So in manipulation, I think Todd alluded to this. The Atlas has 6 degree of freedom arms. It has a lot of holes in its configuration space. For tasks in the DRC, you actually do want Cartesian motion. So you want either the hand or a tool tip, like a drill tip or a wrench or something like that, to move along an arc or a straight line. And that can be difficult when you only have 6 degrees of freedom arms that don't have a lot of motion, a lot of range of motion. In particular, we tried using off-the-shelf IK solvers. So, if you commanded the tooltip to go from one location to another and you create a dense trajectory in Cartesian space, somewhere along that trajectory, KDL or IK fast is going to fail. It's going to say, I can't reach that exact XYZ roll, pitch, yaw pose. So what do you do there? Well, the first thing we started doing was searching near there in Cartesian space. And that requires running a lot of IK solver, running IK over and over and over again to try to find a set of joints that get you close to the pose that you want. And that was actually quite slow. Additionally, because when you're in a drill, some poses can be under constraint. So for a drill, you don't necessarily care what the roll of the drill bit is, and so that's actually quite a large search space in Cartesian space if you want to search all the way around every place the hand can be, but the drill is in the same location. So what we did is we implemented a joint space search instead of a Cartesian space search. So essentially, we try to find Cartesian space solutions that are close enough by searching in joint space. The idea there is that you take the last configuration of the joints, you take the next pose you're going to reach is reasonably close. You then start randomly moving joints in joint space and using gradient descent to decide whether you're moving closer to the pose that you'd like to get to. Use simulated annealing to shrink that search space over time and hopefully arrive at a pose that's close enough. It turns out that this works pretty well. So we went from just trying to search in Cartesian space using traditional IK solvers taking minutes for dense trajectories that were thousands of poses to being able to solve it in seconds. Currently, this has actually led to a new NASA project that I just started to implement this on robots in space whose joints may fail over time, and you may go from 7 DOF, 9 DOF, 8 DOF, or 7 DOF to even lower, but you still want Cartesian-like trajectories. So here's sort of a typical example. If you can see, the green arrow is actually what we want the robot to achieve. IK will fail along here. One of these poses just isn't valid, and so we run our joint space search, and it gives you the red arrows that you can see aren't exactly the pose that you want all the way along the trajectory, but it's pretty close. So that wraps up sort of an overview of some of the very simple, straightforward things that we did, and then I'll go into more about how this translated into success in the DRC. So we came in 6th, as I said. We tied, actually, was it you guys that we tied? Oh no, WPI we tied in points, but we had fewer interventions. You can see, here's a graph from DARPA. On the left is the total number of points of all the teams that participated in different tasks. On the right are our points. You can see that TRACLabs is a prototypically typical team. Our graph looks very similar. Just some strange factoid that one of our people told me that we were one of 3 teams to score a point on every task that we attempted. On every one of these tasks that we attempted. So I have some videos which I'll probably have time for, but I don't want to show them all. But just some of the instances of explaining how that software worked. So here the user is using that wall task, that wall tab that I showed you to define moving the arm a distance from the wall and then following a trajectory along that wall to try to open up the handle, which once they did, then the door opens, we swing the door open through another, just moving the interactive marker and asking the robot to move its arms out to open the door. Then we do a side step in that walking tab that I showed you, and then we just click on the other side of the door and ask the robot to walk through. Just a note, I believe we were the only Atlas team to walk through the doors facing forward. I think all the other ones walked through sideways, if I'm not mistaken. So, there you go. And then I think at the end of this video it gives a little bit more closer idea about exactly what we're doing here to try and use that tab to draw trajectories with respect to the wall to arc the arm. Another note, we did not use hands here because the hands were actually harder to get and wrap around the door handles, so we just used the metal plates that the hands mount to, which worked well. And so here the robot goes, except when it lets go and then the wind blows the door shut. So again, wind was another factor that we didn't, like Lockheed, we didn't anticipate. The debris tasks, so a lot of people, Morris, I know spent 30 minutes diligently picking up debris to move out of the way of the robot so that, ideally it could then go through this area and go through a door. Our idea was, why do that? You have a big honking robot, just knock that stuff out of the way. So that's how we, this is another sort of way that keeps with the philosophy of our team. Just do the simplest thing first. This is all lightweight debris. Why, try to pick it out of the way when you can just bulldoze through it. I'll keep this running a little bit just because the last, let's see, the last bit of this is exciting. So here it goes, it keeps bulldozing more and more. Eventually there's a truss, metal truss, that's holding up that debris. Eventually that truss hits the back wall, and then a movable object becomes an immovable object, and that's not good. So maybe that's a reason why you want to pick the debris out of the way. So there it goes, and we have a bit of a fall there. But in any case, we cleared a large amount of the debris out of the way. And the debris that we didn't clear out of that path was pushed to the sides and would have probably been good for another robot to move through there. The wall tasks, as I said, we used our joint space search and basically defined a smooth Cartesian motion from the middle of one circle to the middle of the other. And the robot then tried to execute that. As mentioned in the previous talk, the controllers on board that Boston Dynamics provided us for the arms didn't necessarily follow what you requested. We've since fixed that up, and I know a lot of people have worked hard on fixing that up since. So there's our point and wall task using our just straightforward wall tab. I won't go into some of these others because they're sort of routine compared to what the other people did. So looking towards finals. So we've improved the manipulation capabilities. So the Boston Dynamics control of arms actually estimates joint positions using the difference in hydraulic pressure, but there are encoders on the joints. So we've since just decided to execute our own closed loop control using the encoders, and we're getting much better quality manipulation. The arms actually go where we want them to. We're using two robotic 3-finger hands now on the arms, which is giving us much more robust grasping ability, especially for large irregular shaped objects, although those hands are rather large, and so they're not as good to pick up small items with. We're working very similarly to what Lockheed talked about with guided autonomy. We're preparing our team right now, laying down the infrastructure to provide more autonomy to the robot, or to allow the robot to take over more autonomy. So we're scripting out tasks, we're setting up executives that allow the robot and user to maintain the same state about where the robot is in a task, and if communications is lost between the user and the robot can take over, and when communications are restored, the user then finds out exactly what the robot was doing autonomously and why. We're also working on full body force control, so the robot is going to need to move to prone positions if it's falling, or safe positions if it's falling, so as to not break hands. It's going to need to get back up if it does fall, and of course get out of the vehicle that it drives in the first task. All of these are going to require a full body control, which is currently not implemented on the robot. And we're hoping that we can, if we make it far enough along that we can replace some of the walking from Boston Dynamics with more precise control of the legs. We've already started detecting known objects, such as drills, and finding grasp points on those objects and comparing those grasp points with stored affordances for objects. And so this is the very first autonomy that we're pushing into the robot so that it can decide to pick up an object that it knows if that's what the task entails. We also are looking at improving the 3D localization the same way Lockheed is so that the robot can walk over large distances. So with the spinning LiDAR and poor odometry, the robot currently has to stop every now and then and refresh its 3D map. And we would like to get away from that, and we're looking at using visual odometry from the stereo cameras to compare to the 3D point cloud in order to do that. And finally, it looks like we're going to unfortunately have to redo our network layer yet again with the new network restrictions of network dropouts. The UDP communications layer is probably not going to be adequate, so we're going to have to move back to a TCP communications layer and re-examine that. And that's pretty much it.
Great. We thank our speakers. Any questions?
So, same question, Mr. Chair. So what, do you have some examples of what you're doing because you think it's threatening to the finals as opposed to being the right thing for general robotics problem?
Yeah, I'd say that our team in particular, because we're sort of just looking at this as a system integration engineering problem, we're going to just go there and try to just solve tasks. And so I'd say out of all the teams, we're probably the least likely to be looking at high-risk solutions or correct solutions or novel solutions to problems. And so we are, we break down every single task and every single step we have to do, and we just look at what can we do to hopefully solve that task 80% of the time.
So you said you were looking for close enough trajectories. Was the issue that there was an actual hole in due to the BDI kinematics, or was it just your IK solver couldn't find the solution?
It's actual holes. So we created a closed loop solver, or a closed form solver for the arm, and there's just lots of solutions that are not solvable for that robotic arm.
Now that you said closed form, what's approach did you take to?
We just use IP fast, so it's an offline program that reads in.
We're familiar with it. We used it too, but we had real trouble with it.
Yeah.
And ended up using iterative solutions.
Yes. So the iterative solutions of KDL actually will work as long as you have tolerances, but they're just slow. And so it turns out that the joint space search was much faster. Especially if your trajectory is dense enough to where your next pose is close enough to your current pose. The search actually will converge pretty quickly.
Can someone read my comments, please?
Sorry, Gil. Gil has quite a few comments, so I've been. I'll start reading from about 20 minutes ago. I guess one question Gil had was whether the issues with the arms were related to just the old arms, or do you envisage any problems with the newer arms?
Well, the newer arms will be 7 degrees of freedom, so I think that that's going to help out a lot. Our configuration space will be much smoother and more continuous, but yeah, so I think that we can probably move back to normal IK solving, although hopefully with the current project I'm working on with NASA right now, we can take this new joint space approach and actually speed it up quite a bit to where we can just replace IK solving altogether for dense Cartesian trajectories.
I guess Chris followed up by saying we don't obviously have these new arms, which I guess, and Gil was asking, are the plans too fuzzy? I would say that at the moment, while BDI are still working through designs, I think the sooner we could get access to URDFs and the robot's ARM configuration, the most beneficial that would be. So if we had that tomorrow, that would be
Right. I
nice.
mean, the nice thing about kinematics is that you can just solve these offline without actually needing a robot, just to, at least to see if you can compute solutions.
And also how good the workspace is.
That's right.
It looks like they did a pretty good job of reorienting the base mounting of the lab to the most proximal.
I think Eric has a question.
Patrick, was there, because you aren't sending the full 3D point clouds to the operator, were there cases, trials, where the operator was lost? Like, what am I looking at, where am I? Or did they have good situational awareness the whole time?
They had pretty good situational awareness. The major issue we had was the fact that what the robot arms told you, where the robot arms told you they were, was not actually where they were. But we've since fixed that by using the absolute encoders on the arms. But the point clouds are fine. They're just a little discretized, so they're a little bit compressed. But we actually had different functions where we could ask for denser point clouds that were close in to the robot. And so when you're manipulating things, it was fine.
All right, great. I think we have to move on to the next slide.
Right, sure.
I think our speaker one more time, please.